Welcome everybody for the second to last session of the week-long AFLOW school here at the TU Dresden. My name is Esters, and I'm a postdoc at the Center for Autonomous Materials Design at Duke University in the Corte-Rural group. And we will now make a little bit of a left turn here and talk about phonons. First, I will talk about the phonons and the harmonic approximation. And then later, after the break, Dr. Smolyanuk will talk about the quasi-harmonic approximation. Phonons are a fairly complex topic, and not all of y'all will probably deal with them or heard about them. So I put a list of textbooks and papers in here that might be interesting for anybody who is interested after this talk, looking at phonons. These are very, very good introductory works. But first of all, I'll start or try to explain a little bit about what phonons are and how we calculate phonons and what they are responsible for. Phonons describe vibrational motions of atoms on a lattice, and also called lattice vibrations. And they are collective properties, so they are not just confined to a unit cell. All our all our sessions before were mostly concerned with a unit cell and not so much concerned about anything that stretches to the entire crystal. But phonons are exactly that. They're stretching out to the entire crystal, and they're responsible for very, very important for physical properties such as thermal properties, thermal conductivity, especially. Professor Tor talked a little bit about thermomechanical properties, and phonons are the basis for these properties. In some cases, electrical conductivity and thermoelectricity and superconductivity, phonons can play an important role, especially in superconductivity. And they also play an important role in phase stability. Phonons can destabilize or stabilize a material. We will talk about it at the end of the session, how they can destabilize, or how we can see that phonons destabilize a material. What is exactly a phonon? Let's start talking about an atom or phonons in a monatomic basis. So just one atom in a unit cell. In this case, an atom has 3 degrees of freedom, x, y, and z, 3 Cartesian coordinates. And there are essentially 3 ways how they can move relative to each other. They can move, if we assume a propagation direction that is, let me get the laser pointer. If we assume or rather a pen. If we assume that we have a wave propagating in this direction here, there's 2 ways how these atoms can move. They can move perpendicular to this propagation direction, or they can move just in parallel of the propagation direction of a wave. And the former is called transversal, and there's always 2. Here in a 2D view, I can only show one of them, but there's always 2 ways to move transversal, perpendicular to the wave propagation direction. And the other one is longitudinal, when the oscillation is in the same direction as parallel to the propagation direction of the wave. What happens when we have 2 atoms, though? There's 2 options here. The atoms can oscillate in phase, or they can move out of phase. Here's a wave where everything is in phase. So they're essentially oscillating in the same way, and here in this case, perpendicular to the propagation direction. And the other way is longitudinal, but also still in phase. So you see, when we go back to the propagation direction of the wave, which is going this way here, we see that there's again 2 options to move along the same direction, and these are all in phase. And these are called acoustic phonons because they behave similar to a sound wave. When you kind of imagine a sound wave, they're all in phase. The other way is, of course, out of phase. If there's something in phase, maybe we can also displace something out of phase. And here again, we have transversal and longitudinal ways to move out of phase. Here we see the transversal out of phase motion, and these out of phase phonons are called optical phonons. And in general, each crystal has 3 acoustic phonons, and the rest of the phonons are optical phonons. Here's a longitudinal optical wave. Let this animation just play out. Okay. So I said we are talking about phonons being properties of a supercell, or of the entire crystal. So we have to introduce some notation about supercells. Let's assume we have just some arbitrary unit cell, and a supercell is really just a, which is now here. This one is the unit cell, and a supercell is really just a replication along its axes, along its unit cell axes. So here, this one here, if we stopped displaying our crystal along this line, this would be the supercell of the unit cell here shaded in gray. And there's 2 important lengths we need to keep in mind. One is that we point to an atom in the unit cell. In this case, we display it as x0 kappa. Kappa is the atom index of the blue atom, and 0 means we are in the unit cell. Some arbitrary index L kappa means that we are pointing to the same atom type, but in a different supercell. This is very, very common to display it this way in phonon literature. And this vector here, XL, just points to the origin of the supercell, and no kappa involved here. And these 3 vectors are very, very important when we actually start quantifying phonons. Here's another example. Here, this atom goes to a different atom type and to a different supercell, so we just call it L prime kappa prime. And here, XL prime points to just the different origin here in the supercell. I'm introducing this because this notation is going to be pretty important when we actually look at it, how we calculate them, which is what I'm going to do next. So how can we quantify, how can we describe these atomic motions, these wave motions in a crystal? This is going to be a little bit mathy, but I hope it's not going to be too mathy. But this is just the assumption that we're going to start with. We have a potential energy which we expand in a Taylor expansion with some coefficient phi and a displacement U alpha. U alpha means this is a displacement. We displace an atom along the Cartesian index alpha, which can be x, y, or z, or really any arbitrary index in a coordinate system. And we just keep expanding this. And for the harmonic approximation, we stop after this term, after the second term here. And are trying to figure out if we can use this to calculate the motion of the crystal. So what is this particular coefficient here and this coefficient here? These are the interesting ones. This one here is just the first derivative of the potential energy, and this is the negative of a force. So if we are in equilibrium, the forces on the crystal is 0. If it's not 0, then the crystal is distorting and we are not in equilibrium anymore. So this term, the first one, is going to be 0 if we are in equilibrium. The question is, of course, what happens if we're not in equilibrium? And that is a very, very important question if we're assessing phase stability. I will get to this at the end. So this entire term here, oops, that was badly crossed out, but this entire term here will be 0. The second term here is the second derivative of the potential energy with respect to displacement of 2 atoms along 2 different Cartesian indices. And these are called the harmonic force constants. And these are going to be central to our problem when we talk about phonons. So when we actually start writing this all down, we just end up with a quadratic term, or with a second order term plus some constant here at the beginning. And this is called the harmonic approximation because it looks kind of like a harmonic oscillator. We can start now just going through the math and trying to solve the equation of motion. We can build the equation of motion. This is going to be in the next 2 slides. For this purpose, it's not too important to understand the exact math right this second, but I put it in there anyway in case you want to review the material, really understand where the terms are coming from. But the 2 slides that I'm skipping, so that it's there. We just start with an equation of motion that is just classic Newton mechanics. Essentially, we have a mass times the second time derivative of a displacement, and that is the negative of the first derivative of the potential energy. And when we start solving that, we end up with this equation on the right, which is an eigenvalue equation. This here is an eigenvalue equation, and understanding these terms is very important. These are the frequencies of your phonons, which are determining a lot of vibrational properties, including thermal conductivity, including vibrational free energies, which can be extremely important for phase stability. Here's an eigenvector, which are very important for understanding how the atoms get displaced. They're essentially describing, to some extent, the motion of the atoms in the displacements, and we will later see how that looks like. And this here is a matrix, and this is the one that we actually need to determine to really solve the eigenvalue problem. It's called the dynamical matrix. The dynamical matrix is defined underneath here. So let's go through that dynamical matrix so we can really understand what is involved and what we actually need to do to calculate and solve that eigenvalue problem. This term here we already looked at in the past. These are the force constants. These are the masses of the atoms, which are already well known because we have a periodic table. We can look at the masses. This one here is a reciprocal space vector that essentially describes the wave vector of that atomic motion wave. And these here I introduced earlier, these are the vectors from the origin to supercells, which are already known. So because we know the crystal structure. So the only real unknown component is are the force constants, this phi that we have in the dynamical matrix. This is the quantity that we need to determine using phonon calculations. Here, as I mentioned, the eigenvector is very important for the atomic displacements. Below there you find the formula. Here it's describing a plane wave with the eigenvalue as the direction, and later we will see how to visualize them for a specific point in reciprocal space. As I mentioned, we need to get the force constants, and here I'm showing you how we actually get to those. So if we just recall what the definition of the force constant is the second derivative of the potential energy with respect to 2 atomic displacements. And here in AFLOW, we are using the central difference method for derivatives. The central difference method has a very important advantage that it can potentially just cancel out any kind of residual forces that we have. And this is the formula. So we're getting the function. We're determining the function when we displace an atom along one direction and it's negative. Applied to the force constants, that means that we take just since we have to get the second derivative, we are displacing one atom along a certain direction and subtract it when we get the first derivative when we displace the atom in the other direction. If we recall that the first derivative of the potential energy is the force, what we end up with is this term here at the bottom. So we are calculating two forces where we displace an atom along a specific direction and measure the force on another atom while we do that. And how can we determine these forces? Using density functional theory. Density functional theory is pretty good at calculating forces. So at the end of the day, we need to use DFT on structures where an atom has been displaced, measure the forces, get the force constants, and from that get the dynamical matrix. So the strategy here is for us, we need to relax the unit cell structure so the forces must be as close to zero as possible. If they are not zero, or if they are large in your cell, you have a lot of noise when you displace an atom from its equilibrium and measure the forces. We need to create supercell structures with displaced atoms because we are looking at the forces on atoms of essentially the entire crystal. Naturally, we cannot display a cell of the entire crystal because that's impossible. But we will talk about it in the last point here of the slide. Then calculate the force using DFT, determine the force constants, and then get the dynamical matrix. And then it's just an eigenvalue problem, which is fairly simple to solve. We can make a few simplifications here. Technically, we need to displace every single atom in the entire crystal, and then we can get a good measure of what the force constants are, but that's not necessary because we have translational invariance in the crystal. If we displace an atom in one cell, or if we displace an atom somewhere in another supercell, doesn't matter. It should have the same. It should have the same impact. So we can already just focus on the unit cell, which is good. And the other thing that we can do is we can use symmetry, which Dr. Hicks has talked about extensively in prior sessions, to reduce the number of distortions. If you displace an atom, for example, in the X direction, and it looks the same as if you displace it in the Y direction, for example, because your system is cubic, it will be a waste of computational resources to just calculate everything. So we can already reduce the number of calculations, as Professor Tora has shown for the AEL-AGL section, to reduce computational resources. And for phonons, this is more important than for really anything, because as I said, we have to deal with supercells. So these cells can be very big. 200, 250 atoms is not uncommon. So how big do these supercells need to be? There's unfortunately not a great answer, or not one answer to fit everything. Essentially, the answer is big enough, which is not a satisfactory answer, but it is unfortunately the answer. It needs to be big enough to capture all the interactions. At some point, your force constants will go to zero. It is unfortunately not always a priori easy to see what that cutoff distance is. And atoms, in the end, should not interact with their periodic images. That's something that we always need to keep in mind when we do density functional theory calculation. It is not just, unlike a molecule, a closed unit. It essentially propagates from one place to the next, and the distortions will also propagate from one supercell to the other. And if these distortions see each other, you will get additional ghost forces in there that will make your calculations very, very inaccurate. So this was a very theory-heavy part, but still, does anybody have any questions about the general concept of what a phonon is? Excuse me. Anybody been able to follow, especially the difference between an acoustic phonon and an optical phonon, longitudinal, transversal, and kind of understood what the strategy is that we need to calculate force constants to get frequencies? We will see in the next session kind of how this looks like in practice and how we get there. I I see a thumbs up. That's great. This feedback is very important. Oh, this is a very good question. I really like this. In theory, couldn't we use the relaxed forces as reference to remove noise? In principle, you could. That kind of depends on how big your noise is. I'm not sure if your background is computational or experimental, but let's assume we have a some kind of measurement where we have some noise, and you do, for example, a background subtraction, for example, X-ray diffraction, where you have a little bit of like a background, a slope background like this, and you can do background subtraction. But if your background subtraction, if your background noise is so big that it kind of starts having a significant impact on your signal, you get a larger error when you do background subtraction. So yes, in theory, you could do so. You can calculate the undisplaced supercell and subtract the forces, and AFLOW can actually do that. But if your forces are so large, you might actually have too much noise for your signal. So it has the same problem as any kind of background subtraction. Great question. I really like it. Any other questions before we move on? And I will show you a little bit how AFLOW handles APL calculations. That doesn't appear to be the case. So we will move on now to the virtual machine. The instructions are in your PDF slide 13, but you can also just follow along. I will post the commands that I'm writing that I'm using in the chat as well. So I'm going to go ahead and share the virtual machine. Let's all go into the exercise directory for day 5 and to session 11, phonons. And we will start the first command that I showed, and that's AFLOW generate AFLOW in only. If you don't have generate AFLOW in only, it will look for POTCAR pseudopotentials, which is which we don't have available here in this machine. Let me move my Zoom stuff over real quick. So AFLOW proto, and the prototype, we just want aluminum's CF4 225A aluminum, and then module equals APL. Let me post that in the chat. This is the one, and it creates an AFLOW in file. We already saw something similar for the AGL and AEL session, and we will just go into the AFLOW data directory, hit tab twice because it's only one directory, and in there we run the AFLOW command AFLOW run or generate AFLOW in only run -d current directory. I should have copied the command before I hit enter. Need to work. Here's the one. So it finishes very quickly, and what I would like us to look at is in this directory, I would like to look at the AFLOW in file. Actually, I can use them. It's a little easier. Looking at the AFLOW in file that was generated first. Go. If you go down a little bit, you see there is that AFLOW-APL calc is commented out, and if we recall the AGL and AEL session, this means we're using an APL calculation. APL is short for Automatic Phonon Library, which is the AFLOW module to calculate phonons. There are a lot of options. I cannot, for the interest of time, go through all of them, but there is, if you do AFLOW -- read me equals APL, you can see what all these options mean. If there's a question about, if there's confusion, you can contact the AFLOW forum for assistance, and I will do my best to update the documentation. But the important options here are, I will mark them. First of all, that it's calculated, and then there's 3 options I would like you to look at. The one thing here is relax on and precision phonons, apprixomation. Apprixomation is not a VASP setting, even though it kind of looks like it. And what it does is it switches from relaxing based on energy to relaxing based on forces, because we want to minimize the forces and not necessarily the energy. And relax on means that when you start running APL and you don't have to generate AFLOW in only part, AFLOW will start a VASP calculation that does this minimization of the forces automatically. And the next one, the next 2 that I would like you to look at is polar on and zero state on. So Raphael asked the question earlier about background subtraction, and the zero state on calculation is exactly for that purpose. It creates a supercell that has no displaced atoms and that will be used for background subtraction. Another way we reduce noise is by using the central difference method, which already has a subtraction implicitly included that might also get rid of a lot of background noise. The other thing, polar, I would like you to just make a mental note that it's there. There's a so-called polar correction in phonons that we'll talk about in a little bit. That is important, very, very important for a couple of compounds. The next thing I would like you to note is that AFLOW has created a couple of ARUN directories. And the first 2 ARUN directories, the APL1 and APL2, are the displacements of the atom. The zero state, as I mentioned, is the background subtraction, the LRBEs for the polar calculation, which I'm talking about in a little bit. In order to keep going, AFLOW will not, if you run AFLOW in this directory, again, AFLOW will not do anything because it's missing data from inside these directories. So let's look at one. Just the ARUN APL, this one here. It has an AFLOW in file. These AFLOW in files are static calculations that just measure the forces on this particular structure. So you need to run AFLOW, i.e. VASP, inside these subdirectories, and then afterwards you can run AFLOW again for post-processing. We'll get to that in a little bit. So now, what kind of structures were created inside? For that, let's open aflow.apl fccalc state out. So I'm just going to write that file name in the chat. And it contains some information about what kind of cell was built. The important parts are here, the supercell. It is a 6x6x6 supercell. I'm not going to go into all the algorithms that we can use to generate them, but here it was a minimum number of atoms. We want a uniform expansion, or as uniform as possible, keep it as spherical as possible to fit, in this case, 175 atoms. That's our default, which often works, but again, you need to test that it actually is enough, or maybe it's too many. And this resulted in a 6x6x6 supercell. The other thing, here's just the structure. The other thing that's important is this one here. This one here is the distortion vector. So here we see this is in Cartesian coordinates, this is in Cartesian coordinates, and we see that it was distorted along the 0, 1 over square root 2, 1 over square root 2. So it was distorted actually not on x, y, or z, but along a phase diagonal. And this is done because we want to have the most symmetric distortions, because the more symmetric our material is in the end, the less expensive are our polar calculations, not polar calculations, our DFT calculations. So this is an important vector to keep in mind. Let's take a quick look at the AFLOW-in file in one of the subdirectories. Especially, I want you to scroll down with a page down button, or if you like edit it, if you look at it in gedit, just scroll down at the structure. You see we have 216 atoms. That's just to emphasize just how expensive these phonon calculations can be. 216 atoms, and you see instead of having an atom in the origin, we have this little displacement here. It's a little bit distorted. The rest is in equilibrium position, but here is just the displacement of this atom. Now I would like you to navigate from here into just 3 directories up outside the AFLOW data, and you see we have a couple of directories. I would like you to go into the aluminum directory. The aluminum directory has a cleaned up version with all the files that we need, and if we look at this, there is an aflow.qmvasp out, which contains the forces of the DFT calculation, and AFLOW will read from this and do the post-processing. You see that there's no zero state and no polar corrections, no LRBE calculation, because for aluminum, these two are not needed. And one is symmetry, the other one is, you will see later why polar was not needed for aluminum. So let's go ahead and run this. This time I will copy and paste this before I get all the messages. So when we run it after there is a QMVASP file in all the subdirectories, you see we have a lot more messaging going on. Here we're reading the force files, and what it does now is it calculates the symmetry of the compound. The force constants have to obey the symmetry of the crystal. And for that, we need to get the site point group for every supercell. This can take a while. Dr. Hicks has shown that our symmetry analysis is very, very thorough, and it can take, especially for very high symmetry structures, quite a bit of time. But I think the accuracy benefit is worth the wait. So after it's done, you see there are a bunch of different files. A lot of them have a certain number of properties. And one of them, for example, that I would like you to look at is the AFLOW-APL Thermodynamic Properties.out. And you see there are a couple of quantities here. One is the 0-point energy, U naught, the internal energy U, the vibrational free energy F, the vibrational entropy S, and the isochoral heat capacity CV. So we can calculate these properties in the harmonic approximation, and F in particular is important because it is actually part of the Gibbs free energy, and in some cases, this can actually change the stability of a material when you include these vibrations, especially when you go from, for example, a low symmetry structure to a high symmetry structure. You can plot these too. AFLOW-plot thermal, and out file, let's call it aluminum. What this does, I will show you in just a second after I place the command in the chat. What this does is it adds a few plots here, a few PDF files, APL, CV for the isochoral heat capacity, entropy, free energy, and internal energy. And as you can see, aluminum here is just the prefix for that. And let's look at one of them. For that, I need to open the file manager and go to my directory. State 5, phonons, aluminum, and let's look at, for example, the vibrational free energy. Here you see it decreases with temperature, and that is exactly what we would expect based on the formulas, which I put in the PDF too, in case you're interested. Another thing we can plot is the phonon dispersions and density of states. Just like electronic contributions, vibrations have a band structure and they have a density of states. And the command is phonon disp-dos for dispersion, which is what the band structure is called for phonons. I'll put that in the chat as well. Here it is. AFLOW plot phonon disp-dos file. Aluminum. Where's the P? I think it's pH disp-dos. My apologies. No, it's not. It's phonon disp-dos. Yeah, that was sorry about that. I need to add the plot. Had a little bit of a I'm sorry, I don't know why I'm out of it. This is the right command. I had it right here. So here, pH disp-dos for phonon dispersion density of state. So let's open the file manager again. Here we see the plot. So just like a band, it looks kind of like a band structure plot with these bands and the density of states. I would also like everybody to note the number of bands or branches, they're called in phonons, that they see. Here it looks like there's 2, but they split. So we have 1, 2, and 3. And that's exactly what we would expect, because aluminum with only 1 atom has 3 degrees of freedom. So the number of branches is always 3 times the number of atoms in your system. If you have more, something went really, really wrong. If you have less, then you probably have degeneracies. The last file that I would like you to look at is the displacement file. Displacements.out. As I said earlier, we can calculate atomic displacements with the eigenvectors, and this file is plotting the mean square displacements. And we can see just what we would expect. If we increase the temperatures, the atoms are moving more and we have larger and stronger displacements. But you can also see that if you look at it, for example, 300 Kelvin, it's 0.009. You take the square root of it. These displacements are very small, but they have a big impact on the transport properties of your system. I'm going to go ahead and switch back to the slides. They contain pretty much the information that we went through, but just for recap, here are the commands that I ran to put aluminum in there, so they're all to run aluminum, so they're all. Okay, there's a question. Can we start an APL calculation from pre-calculated force constants? Yes, you can, because the force constants can be expensive to calculate. AFLOW writes a file called AFLOW.HarmonicIFCs.xml, and if you put your AFLOW.HarmonicIFCs.xml, if you put your force constants into that format, AFLOW will pick it up and read these force constants and then do an analysis based on that. Yes, this was done purely for making it more efficient, but yes, it has the nice benefit of doing that. Ael, the question is, or the comment is, I hope Ael has the same feature. Ael doesn't calculate force constants, so not, I guess it's possible, but stresses. I'm not sure, that's more a question for Professor Tor. Maybe you can answer that during the break or in the chat. These are the plots. Here is the correct command for calculating the dispersion and the density of states. And here are all the commands that you can see in the PDF. If you review this talk today, you will be able to see, or you'll be able to just redo all the exercises. Professor Tor just answered the question about Ael stresses. It can read stresses from pre-existing DFT calculations, i.e. from the outcar. So if you have an outcar, Ael can do the same thing. Here's again the plot that I showed for aluminum. Here's the dispersion, the density of states. These are the formulas in case you're interested in how we calculate the heat capacities and the mean square displacement. I'm not going to go through them. Here are the plots. I showed you the vibrational free energy, but here are also the entropies and the internal energies. Entropy increases from 0, which is great because that's all consistent with physics. And typically the isochoroidal heat capacity in the harmonic approximation converges to 3 Boltzmann constants per atom. And here it's also consistent with the number of cells, because we only have 1 atom in the cell. There's one more quick word I would like to have, one more quick thing I would like to address before we go to the exercises, and that is the distribution of phonons with frequencies. The phonons are bosons, so they follow the Bose-Einstein distribution, and this is the formula essentially here. When we have a small frequency, there's going to be a lot of phonons that are oscillating with that frequency at lower temperatures, and the higher frequencies become more important with higher temperatures. But as you can see, this only starts increasing. There's no conversion of number of phonons here. Rafael asks, is this feature compatible with DFPT outcars? AFLOW, since it is tailored to VASP, can do, APL can do this too, can use gamma point density functional perturbation theory as implemented in VASP. It is when you change engine DM to engine equals LR. And yeah, as soon as VASP releases a version where we can do arbitrary Q-point density functional perturbation theory, we'll start implementing that in APL, but until then we have to stick with gamma point. So yes, it can do DFPT. You're welcome. We are actually using DFPT for the polar calculations, which is why polar calculations require VASP5, not VASP4, because VASP hasn't implemented that at that point. So it looks like it is 17:05 right now, and we'll just go into the breakout rooms for the exercises. There's 4 of them. I would like you to run the post-processing for one of the 4 compounds. It really doesn't matter which one it is. Look at the displacement, and please don't forget to add this line here, the DOS project equals on. You will see later what it means. And determine the average mean square displacements in the isochoroidal heat capacity at 300 Kelvin, which means just look at the output files and note the value. And then I would like you to plot the combined phonon dispersions using this projection equals atoms kind of projection method. The print equals PNG is is print equals PNG is optional. I'm getting a question. There's a module AAPL and AFLOW in. What is this? AAPL is short for the anharmonic, the automatic anharmonic phonon library, and we use this module to calculate thermal conductivity. We are not going to talk about this in this AFLOW school because these calculations are incredibly expensive. Even the post-processing is pretty expensive. So, and we don't have time for it, but yeah, this is essentially what it is. There's a paper if somebody can, are there already Phonon data in the AFLOW database? We are working on getting some of them in. Right now, as of right now, there's not directly, because it takes a while to actually get those Phonon calculations done. Okay, looks like everybody's back. I hope this wasn't too difficult. And if it was, please let me know so I can answer all your questions. Let me share the screen and see where you can get the data. One of them is APL FC Calc State Out. This is probably the more difficult one to find, to look at the displacements that are generated. Here are the two atoms here. 0 refers to index 0, which is magnesium, and it goes along 1 over square root 2, 1 over square root 2 along x and y. So that is a phase diagonal, and the same thing happens for oxygen. Since magnesium oxide is a rock salt structure and just very regularly placed, it's not too much of a surprise that they have similar displacement, but that doesn't need to be so, but often they are. The other properties are found in AFLOW.APL thermodynamic properties out. At 300 Kelvin, it asks for the isochoric heat capacity. It's like 4.54. If you divide this by 2, you get about 2.75 Boltzmann constants per atom. The last property, the displacements, are found in AFLOW-APL displacements.out. And if we go to, let's say, 300 Kelvin, we see that magnesium has a slightly larger displacement than oxygen here. This is for magnesium oxide. So here's for the other materials. We see that magnesium oxide, boron arsenide, niobium carbide have the same displacements. They all go along the phase diagonal. Magnesium oxide, niobium carbide are rock salt, and magnesium oxide is zinc blend. So FCC structures tend to be more distorted or displaced along the phase diagonal. Zinc sulfide, the atoms are along this very weird vector, but if you plug this in and look at it with respect to the unit cells, that this is the body diagonal, or one of the body diagonals where it's displaced. And the other results are found here. We can generally see that lighter atoms in general are displaced more when it comes to lighter atoms are typically displaced a little more. That doesn't necessarily hold true for all of them, because it's not just about the mass, but it is also about the force constants, which depend on the electronic environment and on just generally the stiffness of the bonds. The heat capacities are shown here per atom. You can see that zinc sulfide has a much higher heat capacity when you just look at the values per cell, but we also have more atoms, and they all are below 3 kV per atom, which is something you would expect for the harmonic approximation. It typically converges to 3. Here are the phonon densities of states. If you actually projected it to the atom, if you actually chose projection equals atoms and added the DOS project flag to the AFLOW in file, you will get these types of plots, and they show where in the phonon density of states, and also by extension in the phonon displacement, we have more contributions for one atom. We can make up a couple of trends here. We see that magnesium and oxygen overlap a lot. Magnesium is generally at lower frequencies. boron arsenide has very little overlap. We see that arsenic is at the low frequency spectrum, and boron is at the high frequency spectrum. Zinc sulfide, we have a little bit more of an overlap, but there we have pretty much also complete separation between niobium and carbon, and that is very much a mass effect. When we think about the dynamical matrix, the masses where in the denominator, square root of the product of the masses in the denominator. So we can imagine that a higher mass has lower frequencies as a consequence, and that's generally true. But again, force constants also play a role. It doesn't necessarily, it's not super foolproof, but if you have a strong mass difference, it's very unlikely that they will overlap. And this can be used to engineer essentially your phonon frequencies. By having a large phonon gap, you can also just reduce some scattering processes. Boron arsenide, for example, has a very high thermal conductivity, as one of the reasons for that is that they have strong bonds and they have very large mass differences. Any questions about the exercises? Feel free to raise your hand so I don't move on without you if you have a question. That doesn't appear to be the case. I can get a thumbs up to move on. That's great. So the next thing I want to talk about is the polar. I kept putting it, what's with the discontinuity? That is exactly what I'm getting at. You're probably talking about the discontinuity here, zinc sulfide, or are you talking about the discontinuity here? These are two different reasons why we have discontinuity. Are you talking about the discontinuity at the gamma point, or are you talking about the discontinuity here between, for example, E and L? At the gamma point, this is the next thing I'm going to talk about. There is a discontinuity for zinc sulfide. Yes, that's true. And there is the reason for that is exactly the stuff that I've been putting off for a while, and that's the polar corrections. So the polar corrections, when we think about it, we have strongly ionic materials. Let's assume the atoms here are moving. Here in this case, it's a longitudinal optical phonon. So they're out of phase because they go like against each other. But let's say we have a propagation direction along this line here. And what happens when they get closer to each other? When they get closer to each other, they're out of equilibrium position. They're trying to oscillate back because they're just vibrating along its equilibrium position. However, since they have different charges, there's an additional force between them, like Coulomb interactions. So their oscillation is actually not unhindered. So they're going apart, they're trying to go apart, but the electrostatic interactions pulls them back together. When we're looking at a transversal optical phonon, the electrostatic force is not different from their propagation direction. When they go apart from each other and they're oscillating back, the electric field kind of pulls them together anyway. So there is a splitting between the two. They're not degenerate for strongly ionic materials near the gamma point, and that is called the so-called LOTO splitting. You see that a lot. It occurs at small wavelengths because the long-range Coulomb interactions are very long range, and it especially is much more prominent near the gamma point, not directly at the gamma point, but near the gamma point. And there is a so-called non-analytical term correction that must be added to the dynamical matrix. I put the formula here. What is important is that it depends on two very important material parameter. One is this Z here. That is the effective charge tensor. So we can imagine, this is something that we can intuitively grasp by thinking that the larger the charge is, the bigger is this arrow here. So the more disturbance we see from the regular natural oscillation. And the other one is the dielectric tensor. We can just like looking at the equation, we can see the larger your charge is and the smaller your dielectric tensor is, the more of a splitting we have. So since it is happening near the gamma point and not directly at the gamma point, the amount of splitting depends on the direction you come from in reciprocal space. For cubic, there's no discontinuity because of its symmetry, but for non-cubic systems, you do see a difference in where we near the gamma point. Which is why we see this discontinuity here, because we're coming from different directions. Well, that's a weird annotation, but yeah, we see differences in the direction here, which is where the discontinuity. Can we also cure this by brute force by increasing the supercell size? No, because the harmonic approximation does not include that. You would need to use some other techniques, but not the finite displacement method. That term is just not in the harmonic approximation of finite displacements. But there are other methods where you have random or pseudo-random displacements, and you can do fitting of the potential energy where you include the LOTO splitting. But that's more of like where in that case more in the anharmonic calculation level, which is more expensive. But yeah, we cannot increase the supercell size because the this correction or this effect is by definition not in the equation. And neither do you want to, because actually calculating the Born effective charges is not too expensive. It's actually in the unit cell. So I would rather have a small DFBT calculation with a small cell than a even bigger supercell. Especially because if you're actually going to the wavelength where it is important, the supercell would have to be enormous. So let's look at the actual strength of, or let's look at the effect that we have here. So let's go back into the virtual machine, and for now, what we want to do is change the AFLOW-in file and turn polar off and run it again. Don't forget to rename your log file because you already have a log file in there. I would call it just log with non-polar, and run this again. Oh yeah. Something else we shouldn't forget is the generate AFLOW-in only, so it doesn't even think about trying to run any vast calculations or look for pseudopotentials. So we'll run all these dynamical matrix calculations. But what I'm more interested in showing are the dispersions. So pH dis does say out file quotes MGO non-polar and what else, projection equals atoms. And you will see that there are it has been zipped, so don't forget to annex your old plot. what I want to show you is this is magnesium oxide without polar corrections, and here's magnesium oxide without polar corrections. Let's see if I can get those both of them in the same window. So yeah, we see there's a huge difference near the gamma point when we include or don't include these polar corrections. And depending on which material you chose when you did your phonon dispersions, you will see a big difference or you don't. And to verify that this actually makes sense, we can look at the file AFLOW-APL.polar.xml. And here we see we have very large charges, for +2 for magnesium, -2 for oxygen, which is great because that's what it should be. And we have a fairly small dielectric tensor. So that we see the difference actually makes a lot of sense. And I'm going to switch to the slides again. And when we compare, here's again magnesium oxide, when we compare this, for example, with boron arsenide, we have very small charges compared to, for example, magnesium oxide. We only have negative 4.54, and we have a much larger dielectric tensor. We do see actually some splitting, but it is tiny. If you really squint hard, you see a little bit of a splitting here, but not all that much smaller than for magnesium oxide. The zinc sulfide, you see we have without the non-analytic term correction, we have a huge difference, especially looking here at the gamma point. We don't see any discontinuities here. We do see them here though when we turn on the polar corrections, the non-analytic term corrections, because of that direction dependence of the non-analytic term correction term. Again, it's not right at the gamma point, but close to the gamma point. And we see here we have charges comparable to magnesium oxide, pretty much +2 and -2. And the dielectric tensor here is about 5.7, 5.8. So we have a fairly small dielectric tensor. And when we look at niobium carbide, we also have small charges and a very large dielectric tensor. Niobium carbide is a metal, so we expect to have a very large dielectric tensor. It's a general rule is the lower your charges, the larger your dielectric tensors, the less important is to include polar corrections. So often when we have metallic compounds, we can omit them. If we have elemental compounds like silicon, there's not going to be any charges because there's no electronegativity difference. So we can skip the non-analytic term correction here as well. Any questions about this part of the talk? I don't see any questions or raised hands. So I will move on to talking a little bit more about phonon dispersions, especially what does it mean to have a certain frequency at a certain Q point, or what do these Q points mean exactly? I said way much earlier that we can calculate atomic displacements using the eigenvectors at a specific point in reciprocal space. And these eigenvectors are proportional to the displacement with a certain phase factor. And I would like to show you just exactly how this looks like using an X point. Here's again the formula for this. This is just we have a phase factor here and a time dependent factor, which you can see the frequency here essentially determines how quickly everything the atoms oscillate. And this one here is the spatial dependence of the waves. So basically the periodicity. And this eigenvector is the direction, and it's scaled by a mass. The A is an amplitude factor, which is kind of arbitrary and depends on temperature, or is something that you can just enter. These are the reciprocal lattice vectors of magnesium oxide, and the x point is this half-half zero, this particular x point. There are other x points that are symmetrically equivalent, but for the sake of demonstration, I chose this one because when you plug the reciprocal lattice vectors into that particular coordinate, you end up with a wave vector that is along the z-axis. Like this one here, we see the q vector is along the z-axis. If you choose a different x point, you get a different propagation direction. When we look at this one here, this is how they will oscillate at the x point. You will see that it has a periodicity of two unit cells, and you also see that the atoms are kind of oscillating, especially the oxygen is oscillating parallel to the propagation direction. So we have a longitudinal wave, and it's a little hard to see because the oxygen here is very small, but they are oscillating in phase. So we have a longitudinal acoustic wave. Here's another one. Here we can see it a little bit better. Where the oxygen and the magnesium are going, and they're going perpendicular to the propagation direction, and it looks like they're going in phase. Here we also see the periodicity a little better, but see that they're going essentially in phase, right and left, both go right and left. And that is the transversal acoustic phonon. Transversal because they're perpendicular to the propagation direction. This one here is also a transversal mode, but here we see that the oxygen in red are out of phase with the magnesium. If you look at especially this one here, you focus on the one behind, you see that the oxygen is moving out of phase to the magnesium. Another thing that you notice, especially when you compare this one with the one that we had before, is that oxygen didn't oscillate quite as strongly for the TA and the LA mode, especially in the longitudinal acoustic mode. We see oxygen barely moving. And if you recall the density of states, we saw that the lower frequencies are mostly occupied by magnesium, and the higher frequencies are mostly occupied by oxygen. And that is reflected in the oscillation strengths of these different atoms. Here, going back again, we have, as I said, a transversal mode, and they're out of phase. So we have a transversal optical mode. And the last one that I want to show you is, of course, the longitudinal optical mode. And here we again see very, very strong contributions of the oxygen by these to these modes, and very strong oscillation. The magnesium oscillation is hardly visible, but they are in phase with the oxygen. They're out of phase with the oxygen, and they're going all parallel to the translation of the wave, or the propagation of the wave. So this is a longitudinal optical mode. We can create these. I don't know how much time I have. If I have time at the end, I can demonstrate how to create these images, but I put them in the PDF. So we can do these using XCRSTEN, and AFLOW is able to create scene files with this format. We can visualize phonons with this. You have to determine the point in reciprocal space. In this case, the x point is 0.5, 0.50, and a supercell with which to create these animations. The supercell should be the reciprocal of the Q point. So it would have been enough to create a 2 by 2 by 1 supercell, but I think it's easier to just demonstrate it. Otherwise, you don't get a full animation. But AFLOW has the capability to create scene files using the program Dresden, and you have Dresden on your virtual machine. And if I have time at the end, I will show how to create one of them as a GIF. I said earlier that way at the beginning, right at the beginning, that we have that phonons are responsible for phase stability or responsible for phase instabilities. And we assumed all the time, at least implicitly, that we are in equilibrium. So when we are in equilibrium, the displacements increase the potential energy. Because if it wasn't, if it was decreasing the potential energy, you wouldn't be in equilibrium. It wouldn't be at the energy minimum. So all the forces are restorative, which means that when you displace an atom along its equilibrium position, it will go back. Always. It will always try to go into equilibrium. But what if it's not in equilibrium? What if it is not? What if we have an unstable structure where displacements can actually lead to a more stable configuration? That is possible, that happens. And in this case, the displacement decreases the potential energy and forces are not restorative, which means that they don't oscillate back and forth. They just stay wherever if you get the right displacement. And mathematically speaking, this leads to this omega square, which we have in the eigenvalue equation, to be negative, and the frequencies become imaginary. Here's an example. Titanium is hexagonal, but the BCC titanium is, we can calculate the phonons for those too. Here's the hexagonal structure, and here is what we have for phonons in the body-centered cubic cell. You see there are negative frequencies. They're just displayed as negative. They're actually not negative. They're imaginary. Omega square, frequency square is negative. And that means that we actually, at 0 Kelvin, titanium in the BCC structure is dynamically unstable. It would create a distorted structure. However, at 1200 Kelvin or above 1155 Kelvin, these displacements are large enough to actually stabilize the structure. So these imaginary frequencies are also important or responsible for phenomena like charge density waves. They can be important for spin density waves, and they can determine whether or not a material is stable. They can determine whether or not a material is stable. The problem with these imaginary frequencies is that, unfortunately, if you have a badly converged cell, or if your cell is too small, or if you don't have enough K points, you might get an imaginary frequency. Or sometimes you have some weird cells that produce imaginary frequencies at certain Q points for certain supercell sizes. So you always need to make sure that your cell sizes converge to be sure that your imaginary frequencies are actually real or actually physical, as opposed to an artifact of your DFT calculation. At last, the harmonic approximation, as you saw, is only a second order. For first order approximation, you only have the quadratic term, and we can of course expand it. The quasi-harmonic approximation calculates phonons at different volumes, and Dr. Smolyanyuk will talk about it in the next session after the break, and it can be used to calculate thermal expansion and other mechanical properties. And we can of course include higher order contributions if we just don't cut off the term after the quadratic term. We can get higher order, third order contributions, which includes phonon-phonon interactions, and these are responsible for the so-called lattice thermal conductivity. AFLOW-APL, somebody asked about this earlier, is what does that for third order force constants. You can go even higher, but the higher you go, the more expensive it becomes. And there are also renormalization effects, where you go to self-consistent phonons, which is way beyond the scope. AFLOW doesn't have that feature yet. Anyway, these self-consistent phonon calculations are also very expensive. So the more phonon theory you include, the higher your term is, the computational cost can really explode. But here is a thermal conductivity plot for carbon. For diamond, it has a very high thermal conductivity. And you can calculate this using the AFLOW-APL module. Any questions? It looks like I still have about 10 minutes, so I can use that to show you how to calculate or how to get a scene file. Other tricks that we can do for low symmetry structures like point defects, to do what? To limit the number of calculations. Only really the symmetry tricks that we already have up our sleeves, really. The other option, it kind of depends on, at some point, probably what I would try and do, which we don't have implemented, but if it's like, if you end up on the order of like 1,000 calculations, it's probably better to use a lasso type calculation where you just fit your energies. But there's not really like a big trick unless to include like very low symmetry structures. So you generally a little bit more, the lower your symmetry, the more out of luck you are, is always the answer.